Welcome to the deep dive. Today, we're tackling edge computing. You're
Yeah.
probably hearing that term pop up more and more.
Definitely seems to be everywhere now.
Yeah, so if you want to quickly get a handle on what it actually is and why it's making waves without getting lost in all the tech talk, well, you're in the right place.
hmm
Think of this as your express lane to understanding edge computing's core ideas.
That's a good way to put it. Our mission today really is to explore why edge computing is emerging as this, well, powerful alternative to the standard centralized cloud we've all gotten so used to.
Right.
We'll need to look at where the traditional cloud, hits its limits,
Okay.
and then see how edge computing's basic principles offer, well, solutions.
Okay, so let's unpack that. For quite a while now, the cloud has just been dominant, hasn't it?
Oh, absolutely. King of the hill.
Think about it, these huge data centers, seemingly endless scaling power, pay for what you use, get your stuff from anywhere with internet. It really was revolutionary.
Totally. Streaming services, big company operations, all running on that backbone.
Exactly.
And the core benefits were clear, right? Central infrastructure, scales up or down, cost-effective, accessible globally. Plus, the providers manage so much of the back-end stuff.
Yeah, you didn't have to worry about the servers themselves.
Right. Updates, maintenance. It was, and still is, a very convenient model.
Yeah.
Hugely powerful.
Things are changing. We're seeing more applications that need, like, instant responses.
Yeah.
Self-driving cars needing to react now.
Or industrial robots on a factory floor.
Exactly. And that physical distance between where the data happens and that central cloud, well, it starts to become a real problem. We're talking about latency, that delay.
Precisely. Latency. At its heart, it's just physics, really. The delay caused by the distance data has to travel.
Even at the speed of light.
Even at the speed of light. Over long distances, it adds up. And then you add in, network traffic jams and all the little hops the data makes through routers and switches. That's your round trip time, or RTT. It all contributes.
And those tiny fractions of a second, they actually matter a lot sometimes, don't they?
Hugely. Maybe a tiny lag watching a movie is just annoying.
Right. Buffering.
But for those real-time things, autonomous driving, smart factories, even AR trying to overlay digital stuff onto your view seamlessly, latency can be a showstopper.
A showstopper or even dangerous. You mentioned autonomous cars. Milliseconds could be the difference between stopping safely and, well, not.
Exactly that. Or think about industrial controls. Sensors feeding data back, actuators needing to respond instantly. Delay there could mean inefficiency, waste, or even accidents. The more immediate the need for a reaction, the bigger the problem latency becomes in that purely central cloud setup.
Okay, so latency is one hurdle. What's another?
Yeah.
I'm thinking about just the sheer amount of data now.
Oh, yeah, the data explosion, especially from all those IoT devices.
There's smart thermostat, factory sensors, cameras, billions and billions of connected things, all generating data.
It's a flood. And trying to push all of that raw data up to the cloud, it puts an incredible strain on our networks. Bandwidth just gets choked.
And that costs money too, right? Moving all that data around.
Absolutely. Transmitting huge volumes isn't cheap. Plus, you run into congestion, more delays. It's a bottleneck. Think about one industrial sensor, maybe megabytes an hour. Multiply by thousands in a factory.
Wow, yeah. The scale is massive.
It really is.
And it feels inefficient, maybe? Sending every little bit of raw data, some of which might not even be useful, all the way to the cloud.
That's a great point. Why send everything if maybe only 10% is actually valuable insight?
Like shipping tons of ore just to get a few grams of gold out at the other end.
Excellent analogy. It highlights the waste. What if you could process or filter that data closer to where it's created? Only send the important bits, the alerts, the summaries.
Okay, that makes sense, like a smart security camera.
Exactly. Instead of streaming video constantly, maybe it uses a small AI model right on the camera. To detect something specific, then just sends a tiny alert or maybe a short clip instead of the whole fire hose of data. Much more efficient.
Right. Okay, so we have latency, bandwidth.
Yeah.
What about just keeping things running? Reliability. What if that cloud connection drops?
That's the next big one. Reliability. If your whole operation depends on that single central point, any disruption there, whether it's the network going down, a power outage at the data center, whatever, it can bring everything to a halt.
Everything stops. That's a huge risk for businesses needing constant uptime.
A very significant risk. That single point of dependency is inherent in the centralized model.
And it's not just technical glitches, is it? There's security too.
Yeah.
Putting all that data in one place, Seems like you're painting a giant target.
You absolutely are. Centralizing vast amounts of data, often sensitive data, makes cloud infrastructure a very attractive target for cyber attacks.
Like putting all your eggs in one heavily guarded but still single basket.
Precisely. And the bigger and more complex that central system is, the more potential entry points, the larger the attack surface for vulnerabilities. Plus, you run into complex issues around data sovereignty, where data is stored versus where it's generated, and complying with different regional rules.
Right, if my data center is in another country.
Exactly. And if an attacker does get in, the potential damage, the blast radius, can be massive because so much is concentrated there.
Okay, so we've laid out some pretty significant challenges with the traditional cloud model. As demands increase, latency, bandwidth bottlenecks, reliability risks, security concerns.
Yeah, especially as the world gets more connected in real time.
So the alternative. This is where edge computing steps in.
Yeah.
And it flips the model, right? Turns it inside out, almost.
Exactly. Edge computing is fundamentally about distribution, moving the computing power, the storage, the applications away from only being in those distant data centers and placing them much closer to where data is actually created and needed, right out at the edge of the network.
The edge.
And the whole point is to tackle those limitations we just discussed: latency, bandwidth, reliability, security, head on.
All right, so what are the core ideas, the basic principles driving this shift?
Well, there are several key principles. First, proximity is huge, just putting the compute resources physically closer.
Makes sense. Less distance.
Second, distribution, decentralizing the workload away from just the central cloud. Third, enabling real-time processing right there.
For those instant decisions.
Exactly. Fourth, selective data transmission process locally, only send what's needed. Fifth, autonomy, letting edge systems work even if the cloud connection is down.
Oh, interesting. Independence.
Yeah. And finally, resilience. The whole distributed setup is naturally more robust to failures in one part.
Okay, proximity, distribution, real-time, selective data, autonomy, resilience. That paints a picture. It's like putting mini-brains closer to the action.
That's a good way to think about it.
Now, when we say the edge, it sounds like one place, but you mentioned it's more layered. What does that architecture look like?
Right, it's not just one spot. It's more of a spectrum, a multi-layered approach. Think of it like this. Way out at the very edge, you have the edge devices.
The sensors, the cameras, the actuators.
Exactly. The things actually gathering data or performing actions. Often they have pretty limited processing power themselves.
Got it. The front line.
Then, moving slightly inwards, you have edge nodes. These are beefier. Think gateways, maybe small servers on site in a factory, specialized computers.
Okay, so they can do more.
Yeah, they handle initial processing, filtering, maybe aggregating data from several devices. They're like local supervisors.
Local supervisors, I like that. And then
Then you might have what's sometimes called near-edge computing. Think regional data centers or powerful node clusters serving a specific area. More power than an edge node, but still closer than the main cloud.
So like a middle layer?
Kind of. And finally, you still have the centralized cloud. It doesn't go away.
Okay, still has a job.
Absolutely. For the really heavy lifting, large-scale storage, complex analytics needing massive data sets, training those AI models, managing everything globally, it just receives more refined data from the edge now.
Okay, so it's like a hierarchy. Processing power increases as you move away from the device, but critical stuff stays close.
Precisely. It's about optimizing where the computation happens.
All right, let's connect this back to the benefits. Latency first. How does edge specifically cut down that delay?
It comes back to that core principle, proximity. By doing the processing right at or very near the data source, you eliminate that long round trip to the cloud.
Just cuts it out.
Cuts it out, fewer network hops, less physical distance. The result is much faster decision-making. Huge improvement for user experience in those real-time apps.
So the self-driving car can brake instantly based on its own sensor processing without waiting for a signal from miles away.
Exactly. That becomes feasible, practical.
Okay, latency makes sense.
Yeah.
What about bandwidth? How does edge help with that data flood we talked about?
This is where the local processing and filtering really shine. Edge allows for pre-processing right there.
Cleaning up the data.
Cleaning it up, transforming it, filtering out the noise or the irrelevant stuff before it ever hits the wider network.
Okay.
Edge nodes can aggregate data from lots of devices, sending summaries instead of raw streams. Or maybe only transmit data when a specific event happens.
Event triggered. Smart.
And a huge one now is deploying AI models at the edge. Train the model in the cloud with big data, then run it locally on an edge device or node.
To do what? Make decisions locally.
To do inference locally,
Yeah.
spotting patterns, making predictions right there. Like that security camera example, it analyzes the video itself and only sends an alert if needed. Massive bandwidth saving.
It's like having local intelligence filter the noise and just send the important signals up the chain. That would cut down traffic dramatically.
Dramatically reduces costs, reduces congestion.
Okay, makes perfect sense. Now, reliability. You said the cloud has that single point of failure risk. How does Edge improve on that?
Through distribution and autonomy. Because processing, and often some data storage, happens locally. Edge devices and systems can often keep operating, keep making essential decisions, even if the connection to the central cloud goes down temporarily.
So they can function independently, at least for a while.
Yes. Local data storage means critical info might still be accessible during an outage. Distributed control lets local systems react to local conditions without waiting for central command. And the whole thing is more fault-tolerant. If one edge node fails, it's much less likely to take down the entire system compared to a failure at a central data center.
So that factory you mentioned, its critical machines could keep running on the Edge system, even if the main internet connection is out.
Potentially, yes, for essential functions. That's a massive plus for business continuity, for resilience.
Huge advantage. Okay, last one. Security. How does spreading things out to the Edge affect security? It seems counterintuitive, maybe. More devices to secure?
That's a valid point. And managing security across many distributed devices is a challenge. But edge computing actually offers some compelling security advantages, too.
Okay, like what?
Well, by decentralizing, you're not concentrating all your sensitive data in one giant honeypot. It reduces that massive attack surface.
Spreads the risk.
Spreads the risk, exactly. You can implement security measures, like encryption, much closer to the data source. Data minimization becomes easier to process locally, only keep what's necessary there, reducing the potential impact of a breach at any single point.
Less data exposed if one spot is compromised.
Right. And you can deploy things like anomaly detection right at the edge, spot weird behavior, potential threats, and react immediately locally.
Real-time threat response at the source.
Yes. And finally, keeping data processed locally can actually make it easier to comply with data sovereignty laws and regulations. Keep German data processed in Germany, for example.
Helps with compliance.
It can, yes. So it's about distributed defense matching the distributed compute. But again, it requires robust security management across that whole distributed environment. It's not magic.
Understood. So, summing it all up, edge computing is really about pushing computation and data handling closer to where things actually happen.
That's the core idea.
And doing that directly tackles those cloud limitations we talked about, improving speed, saving bandwidth, boosting reliability when connections are shaky, and potentially enhancing security by distributing risk.
Precisely. It's a strategic shift. Optimizing the whole system by putting resources where they deliver the most value, leading to real gains in performance across the board.
This has been really enlightening, a great deep dive into edge computing.
Yeah.
It really does feel like we're moving towards a more distributed, more intelligent computing world.
It certainly feels that way. The landscape is shifting.
So a final thought for you listening, as we see more processing power and intelligence spread out across devices and local networks, what does that mean? What are the ripple effects? How might this change the balance between the central cloud and this decentralized edge in the future? And maybe most excitingly, what completely new things might become possible with this kind of distributed intelligence that we can't even quite imagine yet? Definitely something to chew on.